Welcome to ISSS session 3 of computational physics with Python. So let us get started. So we will begin from where we left off last day. And today we'll start with exercise 13 from assignment 1 only. And then we will continue today and hopefully we'll be able to complete assignment 1 by the end of 2 hours today. And then we'll be moving on from the next class to the next assignment. If there is time, then we can also do 1 or 2 questions from assignment 2 as well. So let's see how things pan out. But as usual, what has always been my strategy is to take things slowly and explain things as much as I can and break the large problem into smaller parts so that it's easily digestible and understandable. And then we will be able to proceed to the next question. So yeah, and please feel free to interrupt me anytime whenever you have any questions or you are stuck with something. I'll be happy to go over and clear all your doubts before I proceed. Okay, so let me get started. I hope I am audible. If not, please unmute and let me know. I'll start by sharing my screen. Okay, I hope my screen is visible. So let me move in here. Okay, so let's see what this question says. This question is about plotting. It says that in the online resources, you will find a file called sunspots.txt, which contains the observed number of sunspots on the sun for each month since January 1749. The file contains 2 columns of numbers, the first column being the month and the second column being the sunspot number. Excuse me. Write a program that reads in the data and makes a graph of sunspots as a function of time. Okay. So then first thing that we need is the sunspot data. So let's get that data. So here is the repository. So you'll find all the data in the repository itself. So let's go in here and what I'll do is I'll just back. You can download this data anytime. For now, I'll just, for the sake of simplicity, I'll just take this. I'll just copy and paste, but yeah, you can, it's up to you what you do. And let's create one more file. Let's paste this. And let's save this to the same place. And let's change the name to sunspots.txt for, yeah, sunspots.txt. So this will be a text file and let's save it. Okay, so this got saved in the same place where my code is. You will see the name of this thing. Uses I mean, this is ISSS. It's in the same directory as my session3.py is. So that's why I'm able to, if I also go to files, you'll see there is this file which has been created, sunspots.txt. Okay. So as usual, we'll import the NumPy package, which is super useful. And then we'll make a graph, read in the data and make the graph. So for reading in the data, we'll use the NumPy thing. So I will show you what to do. So let's say data equals to np.load txt. So we'll use load txt and we'll give the name of the data file. So name of the data file is sunspots.txt. Right? This is the name of the data file. So let's first see what happens in here by looking at the variable explorer. Okay, so you see, as soon as I ran the code, that there is a variable or an array, which is a NumPy array got created, which is called data. And you see the size of the array is 3143, 2. So what this means is this array, if I double click on it, it has 3143 elements and 2 sorry, 3143 rows and 2 columns. So these are the two things that we have got. So let's close this, go back in here, minimize this for the time being. And then, okay. I'll come in here. Okay. So I'll have this sunspots.txt data, which is loaded. So now the next thing will be to plot this. So it says that write a program that reads in the data. The first part is done, that we have read in the data, and makes a graph of sunspots as a function of time. So let's do that. So for plotting, what we will be using is the matplotlib. So import matplotlib.pyplot as plt. Right. Now we will be using this for plotting. So the way you will access like elements of a NumPy array is something like this. So just to give you an example, say you want to access the zeroth row and first column. So every count in Python starts from 0. So this will refer to, if you look at this will refer to the 0, 0 refers to this value, right? So if you do 0, 0 data, close, sorry, come in here, enter, you get 0.0. Similarly, if you use 0, 1, you will get the first row, second column. So that is 58. And as you can see in here, the element that you see is 58 in here. You can also use something called colon. So for example, 0, colon will give you 0th row and all the columns in the 0th row, right? So if you hit enter, you see you got 0, 58. So this means that you take the 0th row and give me all the columns. So it gave me all the columns in the 0th row. So 0, 58.
So why this 0 dot and 58 dot in the output? Why
Oh,
not?
these are floating point numbers, so that's why.
But then why Python by default considers the floating point numbers and why not integer? Because it looks so, I mean, not so good that 0 point and then 58 point.
So by default, what load txt does is it loads an array whose data type is float 64. So you can assign the data type to be something else, but by default it takes it as float 64.
Okay.
So that's the default setting whenever you use load txt. Okay. So then if you want to get the first column, say you will give colon. Okay, this gives you the same. So colon comma colon gives you returns basically the same thing. So it is exactly the same as the data itself. Now, if you want to get to the first row and all the like the first row, it was, as I was saying it is 0, colon. This gives you the first row. Say if you want to go to the second row, you just give 1 colon. But on the other way around, if you want to get the first column, then what you do is you do colon comma 0. So this gives you the first column. And similarly, if you do colon comma 1, this gives you the second column. So what we want to plot in here is first column against the second column. So first column will be my x-axis, which is time, and the second column will be the y-axis. Okay, so this is what we are going to do in here. So then what I am going to write in here is plt.plot. This is the command for plotting. So we want to first, as x, we want to pass in the first column, and as y, we want to pass in the second column in here. Right. And since we have done this, after we have done this, what we are going to do is we can label. This is optional. So for example, you can label something like a X label, and here you can give some sort of a name in here, say for example, time. And similarly, you can give a Y label, and plt dot Y label. And here you can give, for example, number of sunspots. And unless you will not get to see the output of the plot unless you give show. So at the end of everything, you can give a show. So this will show the plot. Okay. So let me make this a bit large and open the plot window. Here is where you will see the plot getting generated. And I'll hit run the code. And as you can see in here, this plot shows you time on the x-axis and the number of sunspots on the y-axis. It has read the data and it has plotted. So you see there is like a periodic nature in the number of sunspots. So there is a minima and maxima continuously happening. And this is quite interesting. Turns out that there is something called an 11-year solar cycle, which happens where the sun solar activity becomes very high after every 11 years. And this is a result, like the number of sunspots is a direct consequence of increase and decrease of solar activity that people see. So yeah, and so this is just about the data, not much about the code, but about what this data says. Okay. So next, let's go to the next part of it, which says modify your program to display only the first 1,000 data points on the graph. So let's see what we want to do. Here it's asked me to just show the first 1,000 data points. So then that would mean is that what I want is to show the first 1,000 data points. And so that would mean I want the first 1,000 rows. So for that, I'll give something like 1,000 and colon 1,000. So what this would mean here is that you start from the first row and go till row number 999 row. So you go start from row 0 and go till row 999 and all the and take the first column up there. So 0 is the first column and 1 is the second column. And similarly for the second column also, you start from the 0th row and go till row 999. So this colon tells you how long I want to go. And then this will make the plot of only the first 1,000 rows, because that's what the code asks, that the first 1,000 data points is what we need. So now we are going to run this code again. And as you can see, now the time was previously 3,000 and now it has reduced to 1,000 because it's only a part of the data that we are now plotting in here. And this is how you do it. So is this part clear?
Yes, but then how this interval over the x-axis is getting generated automatically? Say this time it is from 0 to 1,000 and the bin size is being decided automatically. Similarly over the y-axis as well.
Yeah, because I have now chosen to plot only the first 1,000 rows of the data.
So what if I want to, I mean, divide this interval, say, in the, I mean, with an interval size of 100, say 0 to 100, 100 to 200, and then so on.
This is the data, right? So x-axis, if you look at the data, okay, I can show you how the data is. Data, the first row is just 0, 1, 2, 3. So that's why since I have chosen till 1,000, so the first row is just the number. So that's why there is it has gone till 1,000 because I've chosen till 1,000.
Till 1000 is fine, but then I'm talking about the interval. Say instead of displaying the values from say 0 to 1000, I mean 0 to 200. I mean in the interval size of 200, I want to
Okay,
display
okay.
in the interval size of 100.
Okay, so for that you need to like there is another option which you can give in here. So maybe I will show it in a much simpler example and then put the example in here. So these are called array slicing. For example, let's create a test array. Uh, this is just a test numpy np array. Oh, sorry, I have to put commas. Okay. So I've created a test array, as you can see, 1, 2, 3, 4, 5. So now if I want this like an output, which will say, so first let's test this simple scenario of something like this. So then what will this will do is 0, 1, 2. It will go till the third element. And if I hit enter, As you can see, it's 1, 2, 3 because I have chosen the 0th element, the first element, and the second element. So 0, 1, 2. So it's 1, 2, 3, right? So now the other way around. So let's try this thing. Let's try something like 1 colon 3. So this means is that start from 1 and end at 2. So then this will show only 2 and 3 because now as you remember, test is 1, 2, 3, 4, 5. So it's 0th element is excluded. So it starts from the first element and goes to the second element. The other way to do it is, say, I go from, okay, so let's see, I go from 1, end at, so okay, let me make an array which is a bit larger so that this is easier to demonstrate. Okay, and now what I want to do is I start from again 1, I go till this, and then I do something like this, right? Okay, so now what you see is that, okay, let's say I go till 7. So then what this would mean is that 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. So this will end in here. So then what this would mean is that it will start from the element 1, which is 2, and it will end at element 6. So 0, 1, 2, 3, 4, 5, 6. So it will end at 7. But I want this as intervals of 2. So it will start from 2, then 4, and then 6. So you see here 2, 4, and 6. So how this slicing turns down to is that you tell the start element. So this is like the start element. Then it is end element plus 1 step size. Okay. So this is the default way of how you would slice stuff. Now, if you do not specify anything, then your start element by default is 0. If you do not specify anything, then your end element is by default array size. And similarly, if you do not specify anything in here, your step size is by default 1. So if you do something like this, it automatically assumes that your step size is 1. So since I've here given something like colon comma 1000, this is same as writing 0 comma 1000 0 colon 1000 colon 1. This is the same thing. But since I am using the default values, so I can just, choose to write something like this. So is this clear?
Yes, thanks for this explanation. However, my question was slightly different and it was related to the display of the graph. So while
Okay,
displaying and over the x-axis, I mean this interval, so I want to keep the data same. However, instead of displaying the over the x-axis, the tick is being marked say from 0 and then 200. So I want to over this x-axis, I want to display it say from 0 and then 100 and then so like here, if you instead of displaying say 1000 records,
got
if you
it, got it. In that graph, you are saying like, since like, for example, here it's 500, 1000, 1500, right?
it has automatically adjusted, I mean, these markers, and
Yes.
I want to intervene, I mean, in the display of these markers somehow.
Okay, so for that, you can use something called plt.xticks. And like matplotlib has its own default way of doing things, but you can obviously change that default way. So if you want ticks at intervals of 100, so you can use something called xticks. So matplotlib has a very large, well-documented thing, and there will be lots of online helps available. For example, there will be something called xtick, xtick interval matplotlib. I mean, most of this is not something that you would remember. Like whatever you need, the idea here is to just you Google it, and at some places you will find something like this. So for example, here you can explicitly set the text like this. This is just an example. For example, let's take this and then let us go back in here. And if you want the text at intervals of say 100, let's here's this. So what we want is say we start from 0. We want to end at say the max of the array that we have, np dot max of the data thing. So let's say data colon 1000, sorry, 1000 comma 0. And we want it at intervals of say 100. So you can very well do this. And let's see if this works or not.
PLT is
Yeah, sorry. Yeah. And so you see it is now at intervals of 100.
Yes, yes, yes.
So yeah. So there will be a lot of matplotlib commands in which you can customize matplotlib. For example, there is something called plt.grid. If you use something like this, then and play it, you'll see you have a background grid created. Then there can be grid line styles, line colors. So many things out there. So you'll have to like experiment with this and see what fits your purpose for the specific thing that you are interested in.
Yes.
Okay, so let's move on to the next part. Modify your program further to calculate the plot and plot the running average of the data defined by this for where r equals to 5. In this case, have the same program plot both the original data and the running average on the graph, and again over the range covered for the first 1000 data points. Okay. So let's calculate the running average part. Then let's keep this, sorry. The same. Let's get rid of this for the time being. And now let's calculate the running average of this. So the running average formula tells me that I find the average of 5 data points each. So I go, so rather it says like if R is 5, then 10 data points. So I go by first 10 data points, average it, and then the next 10, next 10. So I average it by every 10 data points is what this tells me. Okay, so let's do that. So for, let's see what's the best way to do it. For example, if I want to take the R number of data points, so I'll start from say R will be 5 for me, which is the running average number. So I start from R and I'll go till, so it's kth average, it says. So it goes from K minus R to K plus R. For K in range. So it will start from 0 and will go till the size of the array. So this is to get the size of the like the number of rows in the array. I can do something like a data.shape. So for example, let's see. Let me tell what data.shape does. So if you do data.shape, it gives you how many rows and how many columns there are. So I want to go by the number of rows. So I just go to a data.shape 0. This gives me the number of rows. And I want to start from 0, go till data.shape at steps of 2 times. R. So this is like 10 because 10, for every 10 elements, I'm averaging it, right? And then Y AVG. Let me call this Y AVG. And this is first. To start with is just a list. So what I do in here is I do Y underscore AVG dot append. Here I want to append something, and the thing that I want to append is the running average, right? So let's calculate the running average. The running average is 1 by 2 times R, as the formula says. And then let's give it dot. And once I have found this, we have to sum this. So for that, we can use np.sum, which just adds elements. So we'll start from the value of k, sorry, from data. So this is like the data which we want to have. So this will be like, we will start from the kth element because case that is where we start the data, and we will be going till the k plus 2 times R, because there are 10 data points which we are going to average, and we have to include everyone, and colon comma 1 because, sorry, this is the second row on which we are doing the average, right? And similarly, the X averages are also average values. So we take the, say, the midpoint of all this. So we do something called X AVG dot append. So here we are going to append the element which is at the center of it. So that will be K plus R. And here we are going to just append this. Okay, so let's see. It says invalid syntax. Let's see if this is the one which is complaining or not. And we'll know it's a problem here. Oh, got it. I missed the multiplication sign in here. Got it. Okay. So this is how we do it. So let's try to test this and see if this is working or not. So next is the other plot. And let's do this for data. Sorry, here we are going to plot X underscore AVG, comma, Y underscore AVG. Okay, so this must be some, this is a running average, some kind of a smoothened version of the other is what I'm expecting. So let's see if this code is working or not. If it doesn't work, then we will try to debug this and see. Okay. So it says we are out of bounds, and that is because I think what's happening is we are hitting the end. So it's not 3145 is not divisible by 10. So we are taking every 10 elements. So at the end, the number of elements is less. So what we have to do in here is go till the min of this. And let's not make this complicated, but have end element computed separately. Okay, so we want the two things, this and the mean of data dot shape 0. So when we are at the end, we want we do not want to go till the end of it, but do something like this. So that this will ensure that the last element is properly dealt with, right? And therefore, then this average then will correspond to fewer elements and not just 10 elements. So that is something which we also need to take care of then. So the way we will do this is, let me get rid of this notification. Yeah. So the way we will do this for the last is modify this then. And let's see how we can do that. Okay. So we will do elements. So this will give me the number of elements that are there. And this will be the elements on which we are doing the average. So then this R will be then elements dot shape 0, right? So and we get rid of the 2. So this now will automatically have 10 when the total number of elements is 10, but we'll be having something else when the total number of elements is not 10. And then this is easy. And here we'll just do elements, right? And now let's see if this code works or not. Okay. Oh, the same thing has happened for this one as well. So we will do something for, we have to do something for X as well. And for that, we can simply use something like min of k plus r and end, right? And then 0th element. Okay. Let's see. Something is happening here. Let's try to figure out 3143 is out of bounds for. Okay. So since okay, so since this is like the data that we want, so and since our count starts from 0, so what we have to do is we do something like the fifth element is like the fourth element. So we have to be like the fifth element is 0, 1, 2, 3, 4. So it's as an index of 4. So there has to be a -1 to it. And here it is. So as you can see, what happened in here is now we are able to smooth the data by averaging over every 10 points. And this is exactly what has happened. So this, I understand that parts of this code was a bit tricky. So please let me know if there are any doubt that you are having.
No, this is more or less clear.
Okay, got it. Okay, so now that we have done this running average of every 10 elements, what the next part asks is to do the same thing for just 1,000 data points. So for that, 1,000 is easy because now it is divisible by 10. So we will not have this weird thing that at the end we have a few numbers which is less than 10, and then the average has to be done for those numbers. So 1,000 is actually easy. So what we will do is we can slice the data right at the beginning. So we can do data equals to data, and we just want the 1,000 elements and all the columns. So we first just want the 1,000 rows and all the columns. So just kind of right at the beginning reduces the data size and does the same thing. Okay, so now this is the same thing, but now since the range is less, you can really see how the averaging has smoothed the data out, which is otherwise quite a noisy data. So what averaging does is it allows us to smooth a data, and then this allows us to find derivatives very easily, because if the data is not smooth, then the derivatives that you calculate are not realistic, and you will have very bad values for the derivative. So if you want to find out the numerically differentiate any curve, it's advisable that if the curve is pretty noisy, you smooth it out over multiple data points. So I hope this is clear that how this smoothing is working.
Yes.
Okay, great. So now then we can proceed to the next part. So just like before, as I was keeping NumPy import unchanged, I'll now also keep the other import matplotlib import unchanged as well, because many part of the subsequent questions will include graph plotting. Okay, so now it asks us to plot something called the deltoid curve, which is parametrically defined by these equations. So let's look at these. So make a plot of the so-called deltoid curve, which is parametrically defined by x equals to 2 cos theta, some equations. We will write that in for sure. And where theta runs from 0 to 2 pi, take a set of values of theta between 0 and 2 pi and calculate x and y for the equations above, and then plot y as a function of x. Okay. So let's have something called theta, which will run, we can do from, we will use something called linspace, which just gives you equal number of points. So we will start from 0, go till 2 pi, so 2 star np dot pi, and then we will go till like let's say 1,000 data points. So we want 1,000 equally spaced data points between 0 and pi, right? So now we can use numpy, and the good thing about numpy is that you do not have to use for loops. So what I mean by this is that, so let's first write the code and then I'll explain. So 2 star, now we will do something called np.cos theta plus np.cos of 2 star theta. Yes. So now what this would mean is that since theta is an array, it is going to, okay, so first let me remove all the variables that were from the previous, yeah. And now if you run the code, you'll see that theta is an array. So let me run this code for now. Yeah. So you see theta is an array of 1,000 elements. And now when we are using such a function, so you see there is a function which says 2 cos theta plus cos 2 theta, the function like this. It automatically makes the makes x an array of 1,000 elements as well, right? So you do not have to use a for loop and go through every element of theta to create every element of x. So this is something called vectorization in NumPy, and writing vectorized code is very good because under the hood there is a for loop, but this for loop is getting executed in C, because all these functions of NumPy are actually C codes, which are pre-built and pre-compiled in the C programming language, which makes it very fast. So it is advisable that whenever possible, one should avoid loops in Python, especially very large loops. Okay. And this is one of the advantage of using NumPy arrays. Similarly, let's choose y. This is 2 times sine theta minus sine 2 theta. Okay. So now we have x and y's. So the idea is here is to then just plot it. So we'll just do same as before, plt.plot. So plot x and y, and we can do plt dot say x label just to label stuffs. We'll just call it x, get rid of this, just plt dot y label, call it y, get rid of the other parameter that we don't need. You can also make a grid if you want, and then do a plt dot show. So let's open the plot tab and run the code. And as you can see, the graph got created. We have x and y, and we have that deltoid curve. Okay. So taking this approach a step further, one can make a polar plot of r equals to f theta for some function f by calculating r for a range of theta values and then converting r and theta to Cartesian coordinates using standard equations. So we know that in polar, like from polar to Cartesian, the conversion is, so let's then, we will modify parts of the code in here. So we know that from polar to Cartesian, the conversion is x equals to r times np dot cos theta, and y is equals to r times sine. Sorry, I missed an np dot sine theta. Right? This is what we know. Now what we have to define is define r. So the function is r as a function of f of theta is what we are want to use. So here use this function to make a Galilean spiral, which is r as theta square. So then we can do like r equals to theta square. So this is in like a function in polar coordinates, which relates r and theta. But once we have related r and theta, we can obviously always convert r and theta to x and y's, which we can use to plot. There are also plotting modes in with matplotlib, which instead of giving x and y, you can directly plus r and theta, but that is called a polar plot. So I'll not go into that. But if you're interested, I will try ask you to kind of have a look of how you can directly use polar plots where you do not need to have something called x and y. Okay. And it says for me to go from 0 to 10 pi. So instead of 2 pi, let me give it 10 pi, and let's also make the number of points a bit large. So let's have 10,000 points. Yeah. And yeah, so let's try to run this code then. So yeah, you see we have created a spiral. So this is the Galilean spiral, which is r as theta square. So using the same method above, make a polar plot of the phase function, which is a bit more complicated function, which we want to go to 24 pi. So again, we will just give, instead of this 24 pi. So let's just also make this large so that we have enough number of points, and this is like very closely sampled. Otherwise, like you'll have very jagged curves if you do not have enough number of points. So we want to keep that. So now r equals to e to the power of cos theta. So let's change this then. So it's an e exponential of dot cos of theta, right, minus 2 times dot cos of 4 times theta plus sine theta by 12 to the power of theta by 12. This entire thing to the power of 5. Yes. Let's see. Yeah, this will be not sine, but np dot sine because it's part of the NumPy library. Okay. So once we have done this, I'll make this so that this is visible. And again, run this code. And here it is. We see that the phase function has been generated just like that. So before I move on to the next question, is it all right? But I've covered in here.
Yes, this is okay to me. However, I have a problem in the previous graph, wherein
Okay,
the wherein the x levels have been shown. Yeah, this one minus 750, 500. So
right.
how is this possible? Can we have such large values for the expression?
Yeah, sure, you can. I mean, it is just the function of r. Let's see what r is theta square, right? So you had like really large values of theta, and then we just use r equals to x equals to r cos theta and y equals to r tan theta, sine theta, and r goes as theta square. So it generally will give you something like this. I mean,
Okay,
if you just do the math for different values of theta, you'd see that actually you'll get something like this.
okay.
So yeah, so this is I think expected.
So I mean, using the linear space, we are creating 50,000 points. No, we are creating 50,000 points or what? We are creating 50,000 points in the range of 0 to 24 into 5.
Yes,
Okay, so these many thetas would be there.
exactly, exactly. And then we are creating r according to some function, which was like for this spiral, it was theta square.
Yes, yes, yes.
So
And the
since
value.
r is theta square, the value of r becomes very large, right?
Oh, I see. Yes.
Like say, for example, if it is say 2 pi, then it is already 9-ish, around 9, right? And then you do a square of it, it is already then 81. So then your r, the size, you can think of r as the distance or radius of a circle, right?
Mhm.
So then the radius is already 81 for just 2 pi. And for in the previous case, I think we went till 10 pi. So 10 pi will be then around 30, right? If your 10 pi is around 30, and then if you do theta square, then it will be around 900.
Okay, yes, yes. It's clear.
Your R is, since your R is around 900, you see that the graph roughly goes around that value.
Yes, yes.
Okay, so let's try the next one. It shows, okay, there is a file in the online resources called stm.txt, which contains a grid of values from scanning tunneling microscope measurements of the surface 111 surface of silicon. A scanning tunneling microscope is blah, blah, blah. So let's, you can read this at your spare time. The end result is a grid of values that represents the height of a surface, and the file is stm.txt, contains just such a grid of values. Write a program that reads the data contained in the file and makes a density plot of the values. Use various options and variants you have learned to make the picture that shows the structure of the silicon surface clearly. Okay, so let's first grab the data. Where was the data? In here, yeah. So we can go in here. This was, I think, question number 15. So there's this stm.txt. So all I'll do is I'll just copy the, okay, view the raw file. This is a bit large. Just copy this for the time being. It takes a while. Okay. And now I can save this to something called stm.txt. Okay, so just to be sure whether the file got created, I can go to files and see, yeah, it has been created. So we can, and since this is in the same directory as my Python files are, I can just directly call it. Okay, so then we will use the same thing. Data equals to np.txt stm.txt. This is file that we want. And then let's get rid of these and run the code. And you see that the data, so again, this is like a 2D array, and this is quite large because it is like a information of a surface. So we will get to know what it is. But you see the size of this 2D array is it has 663 rows and 676 columns, so quite a large data. So now what we are going to do is we are going to plot this. So for plotting this is a 2D array. You can plot the 2D array by using something called p-color mesh. And in that, you will pass directly the data itself. And you can pass the CMap. So this is the color map which you want to pass. And there are a lot of color maps available. So let's go in those. You'll see if you type something like matplotlib color maps. Allow this. You'll see that there are lots of different kinds of color maps that you can use. And this is up to you, like what you want to do. For example, in this specific case, we can choose something like an Inferno, but yeah, it is really up to you. So yeah, so I'll do something like Inferno and plt dot show. This will just show the thing, but I also want the color bar to indicate the levels. So I'll just do, excuse me, something like this. And then let me run the code and have the plot ready. And there it is. So you can see the color bar shows you on the right shows you what are the values. The color assigned to these different values. And then you see something like this. So this just shows you the surface of silicon. So the data was like the values at different XY points. So the values at different XY points, like at every value of X and Y, there was some value. And that value is in this data thing. So this is like, and the total number of values was 663 times 676. And so that is exactly what it's plotting in here. And this is how the silicon surface here looks like. Okay. So is this clear?
Yeah, so what this mesh here is?
Sorry, what is?
What mesh here is?
Oh, the mesh here, you mean the XY, the values is 0, 100, 200, this thing.
No, actually, you have used this. You have called this function p-color mesh,
Okay,
and
okay.
earlier also, I mean, sometimes I vaguely remember, but I heard the term like mesh grid kind of a thing, which is
Uh-huh.
frequently in
Uh-huh.
that broadly. So I
Okay.
don't understand its meaning.
Right, right, right. So there are two options, P color and P color mesh. So what P color, the difference between these two is just purely computational. So there is some optimization which happens when you want to plot the 2D data. So if you have very large 2D data, then it's advisable to use P color mesh instead of just P color. It just is some kind of like it on in the background creates a mesh on which it interpolates the data, which is computationally cheap. But you as an user don't have to worry about what's going on. All you have to note is that if your data is too large, instead of using P color, you use P color mesh. So this is it. But mesh grid is something different. It's a different Python NumPy function, which I hope we will be using at some point later, but not right now. So it's like mesh grid is useful for creating 2D arrays on which we can make 2D functions. For example, this is an example of a 2D function, but if you have different values of x and y, and if you want to have a function based on the values of x and y, like a two-dimensional function, then one would use something like a mesh grid, which we perhaps will come to later when we are discussing the other examples.
Okay.
Okay, okay. But one thing to clear here is that mesh grid, which you were saying, has nothing to do with p color mesh. Two are completely different functions.
Okay.
Okay, so let's go to the next question, which is about deterministic chaos and the Feigenbaum plot. So let's see. One of the most famous examples of the phenomenon of chaos is the logistic map defined by this equation. For a given constant r, you can take the value, say x equals to half, and you feed into the right-hand side of this equation, which gives you a value of x prime. Then you take the value and then feed it back into the right-hand side of the equation, which gives you another value and so forth. This is called an iterative map. You keep on doing the same operation over and over, for your value of x with one of the three things happens. One, the value settles down to a fixed number and stays there. This is called the fixed point. For instance, at x equals to 0 is always a fixed point of the logistic map. You put x equals to 0 on the right hand side and you get x prime. Let me get rid of this. Uh, you get x prime equals to 0 on the left. It doesn't settle down to a single point, but it settles down into a periodic pattern rotating around a set of values such as say for 4 values, repeating them in a sequence over and over. This is called a limit cycle. It goes crazy. It generates a seemingly random sequence of numbers that appear to have no rhyme or reason to them at all. This is called deterministic chaos. Chaos because it really looks chaotic, and deterministic because even though the values look random, they are not. They are clearly entirely predictable because they are given to you by one simple equation. The behavior is determined, although it may not look like it. So write a program that calculates and displays the behavior of the logistic map. Here's what you need to do. For a given value of r, start with x equals to half and iterate the logistic map equation 1,000 times. That will give you a chance to settle down to a fixed point or a limit cycle if it's going on. Then run for another 1,000 iterations and plot the points r, x for r, x on a graph where the horizontal axis is r and the vertical axis is x. Okay. Let's first write the function there. So def x prime, we will start with, we'll pass x and r, or rather we will pass r and x in here, right? And then what we are going to return is r times x times 1 minus x. Okay. So now let's see what the first part does. It says start with x equals to half. So let's write x equals to half, which is 0.5. And iterate the logistic map equation 1,000 times. This will give you a chance to settle down and then run for another 1,000 iterations and plot the points r, x on a graph where the horizontal axis is r and the vertical axis is x. Okay, so we have to try different values of r, I guess. Repeat the whole calculation for the values of r from 1 to 4 in 1,000 steps, plotting the dots on the same value of r. Okay. So we want to do for r equals to 1 to 4 in steps of 0.1. So np dot a range will start from 1, go till 4 in steps of 0.01. Right? Was that it? Okay. So this is what we do. So what arange would do is that it is similar to numpy dot linspace, but except that in linspace, what you do is you tell the start and the stop and the number of points, whereas in arange you used to tell start and stop and spacing between any two consecutive points, and then the number of points is automatically determined. But all of these, both of them generates numbers which are equally spaced. So now we will do for r val in R. So we'll take each and every values, and for that we will generate, say, x vals, which is we go it for 1,000 times as far as this question says. So let's first do something like for I in range 1,000, because we will be generating 1,000 values of this. And we will start with x vals equals to the first element is x, because that's what we start with. Let's call this x0 just to be unambiguous, and because it's the first point. So we'll start with x0, and then at every point, what we are going to do is we are going till 1,000. So we are going to do something like this, and then we are going to call xvals.append, and then we do something called we will call x prime. That's the number we call. We call it with the value of r is r val, and the value of x in here is x vals I minus 1. We call it with the previous value, right? So every time we call x prime with the previous value of x. So we start with x0, and then every previous value is what we call. Okay. And once we have done this, we have generated a series of x for all the for any particular value of r. So what we do is we do a plt dot plot. So the values of r is along x-axis. So r times, and then, okay, so before going to x vals, after coming out, we will convert the x vals to a numpy array so that we can use the numpy functions. So previously it was a list, and now we convert it to a numpy array, something like this. And then we will use something like r times np dot once like x underscore vals. I'll explain what this means, and then we will plot x underscore vals in here, and we will plot it with O. So what this O means is that we do not want lines in between the data points. So we'll just use dots. So that is what this O says. So we plot with O or dot. Okay. And I think this is perhaps it. Then we can just do something like a plt dot x label, y label, x, and I think x label is r actually, and we have all the different values of x along the y-axis, and plt dot grid if you want a grid, and then plt dot show for showing the graph. So let's see. There is some problem that has happened in here. R. Oh, sorry, it will be R val. Okay. So yeah, before I actually run this, let me explain what is happening in here. As you can see in here that when you are plotting, you have to pass two arrays which are of the same size. So the number of elements in X must be equals to the number of elements in Y. And since R_val is just a number, what np.onceLike will do is create an array which just one and have same R assigned to it. So for example, let me give an example. Test equals to say np.array. I create an array which is 1, 2, 3, 4. So let's create this simple array. So now if you give test, you'll see this array that has been created. So now if I do np.once underscore like, it will create an array and pass test to it. Then it will create an array of the same size as test, but every element will be 1. So for example, this. So you see it creates an array of 1, 1, 1, 1, 1. And now if I multiply 5 to it, what this will do is it will create an array 5, 5, 5, 5, 5. So what I've done in here is for all the values of X, it is at the same value of R. So I want to create like populate the point of all the X values with the dot for the particular value of R. So along these points, all the points are vertically placed at one particular value of R. So that's why I've given R_val times onceLike. So let's see. So as you can see in here, this plot has been generated in this case. So this clearly shows you something like this limit points and things like this. So let's, for example, let's do a KO or K dot. We do not want so many colors. So let's have, just for simplicity, have something in black only. So K stands for actually black, and dot or O stands for like we do not want any lines. We just want the points to be plotted. Okay. So here, for example, you can see for around the value of R equals to 2, whatever value of X you choose, the value, if you start from n X equals to half, and then all the values of X settle to one particular value. So in this diagram, this is kind of the stationary point. While in the other case, here, you see there is a limit cycle because all the values of X oscillates between just a few points. And then later on, after say around 3.6 or something, there are infinitely many values of X. So X kind of passes randomly through lots and lots of values. And this is where you have this something called this deterministic chaos. And this is also called, as you know, is a Feigenbaum plot. So I'll not go into the details of the physics of this. This has to do with this nonlinear dynamics and chaos theory, where you have these kinds of things propping up. So is this part clear?
Yes.
Okay. So based on your plot, at what values of R does the system move from orderly behavior to fixed behavior? Okay, so this we have already discussed. Okay. Then let's go to this Mandelbrot set. The Mandelbrot set is named after its discoverer, the French mathematician Benoit Mandelbrot. Is a fractal an infinitely ramified mathematical object that contains structure within a structure as deep as we care to look. The definition of the Mandelbrot set is in terms of complex numbers as follows. Consider the equation z prime equals to z squared plus c, where z is a complex number and c is a complex constant. For any given value of c, this equation turns an input number z into an output number z prime. The definition of the Mandelbrot set involves repeated iterations of this equation. We take an initial starting value of z and feed it into the equation to get a new value of z prime. And then we take that value and feed it again to another value and so forth. So this is almost the same as this Feigenbaum plot which we were doing. The Mandelbrot set is the set of points on the complex plane that satisfies the following definition. For a given constant c, start with z equals to 0 and iterate repeatedly. If the magnitude of z is of the resulting value is greater than 2, then the point in the complex plane at the position of c is not in the Mandelbrot set, otherwise it is in that set. Okay, so we know that then mod z is less than 2 is what is in the Mandelbrot set. And we will start with z equals to 0. And what's the complex number? For a given complex number c. Okay, so we have some value of c. In order to use this definition, one in principle have to iterate infinitely many times to prove that a point is a Mandelbrot set. Since the point is in the set, only if the iteration never passes mod z equals to 2 ever. In practice, however, one usually just performs some large number of iterations, say 100, and if mod z hasn't exceeded 2 by that point, we call that good enough. So write a program to make an image of the Mandelbrot set by performing the iteration for the values of z for all the values for all c equals to x plus iy on an n cross n grid spanning the region where -2 to +2 and y is also -2 to +2. Make a density plot of the points which are inside the Mandelbrot set are colored black, while those outside are colored white. The Mandelbrot set has a very distinct shape and looks something like a beetle snout. Okay, so let's then do this. For doing this, we first have a code which determines whether a function is in the Mandelbrot set or not. So let's get rid of this. Is Mandelbrot, right? And for that, we have to pass a value of c. I guess it's a value of c, I guess, which we are going to pass. So this is the value of c, which is what we are going to pass in here. And here, for example, we are going to iterate it over for 100 times. So say so let's say n equals to 100. We can change this later on for I in range n, and we will do z square plus c, right? So z is 0 plus 0j. So there is a way to define complex numbers in Python, and you can use j for this for such a purpose. So for example, say if you want to denote a complex number 2 plus 3j, then this is a complex number itself. So this means the real part is 2 of that complex number and the complex part is 3. So this is the shorthand of like Python supports complex numbers like this. You can also do this like separately, like by keeping track of the real and the complex part, and then do the other things yourself. But both of these will work. So now something like ABS of this also works. So for example, say you want 3 plus, where is it, plus in here, 4j, right? So if you want to find out the absolute value of this complex number, you get 5. Because if you recall the complex formula, the complex formula is actually np.sqrt. The absolute value is real square, which is your 3 square, the plus your imaginary square, which is your 4 square. So it will be something like this. So if you are which also gives you 5. So if you are not using complex numbers like j's, then there is no nice way of doing this. So you have to do this manually. So I prefer using j, but it's completely up to you how you would do it. Okay. So now we do something like z equals to z prime, let's say. Z prime as, again, to start with, I also define this as in the same way, 0 plus, sorry, plus 0j. And I just define z prime is equals to z square plus C. C is the number that we are going to pass in here. And so once we have done this n number of times, if absolute value of Z is less than 2, this is the test that we do, then we are called it is to be most likely, let's see. Then we are going to return, okay, command X. We are going to just return this, right? So this will return true or false. If absolute value is less than true, then this is going to return true. If the absolute value is greater than true, then greater than 2, then it is going to return false. So this is the idea of a is Mandelbrot thing, right? So once we have done this, what we have to do is we have to create an array of points for different values of C, and we have to find out whether each of those points are in Mandelbrot or not. So for that, we are going to use first X and P dot linspace. So we are doing starting from -2 to +2. So -2 to +2, and then we are having, say, 100 points, right? Similarly, Y is, say, np dot linspace, again, say -2 to +2, and say let's have 101 points. The reason I'm doing this is then we can clearly distinguish between X and Y's, because otherwise the values will be same. It becomes a bit difficult to decode and debug the problem. So that's why it's advisable to choose the number of points unequal. So once I've chosen X and Y, here I will use the mesh grid. So because now I want to use all the combinations of X and Y. So now what I'll do is I'll have a mesh grid of X and Y. Okay. So now what this does, what mesh grid is doing is with every value of X, it is assigning all the different values of Y. So now I can create like a 2D mesh with different values of X and Y. So this is exactly what mesh grid does. So this is what I was talking to earlier. And now you see a working demonstration of this. Okay. So now it says that you will probably find it useful to start off with a coarse grid and make a density plot. So now let's construct C. So then C is equals to XX plus, plus J by Y. This is the complex matrix that we are going to have. Let's see, this is some kind of a problem in here. So no, I think what I understand what has happened. So we are now going to find out the Feigenbaum plot for every X val. So let's call it Mandelbrot is equals to np dot zeros underscore like xx. So now what this will do is this will create a 2D matrix, because xx and yy are 2D matrix. All the x and y are 1D matrix. For every value of x, we have used all the values of y, and then go to the next value of x, and then use all the values of y. So xx and yy are 2D matrices. So I first create a Mandelbrot function, which is 2D matrix, and then I will go through each and every element of Mandelbrot, which will allow and will assign either 1 or 0, depending upon whether it's part of the Mandelbrot or it's not part of the Mandelbrot. So this first part is just creates the array, 2D array of just zeros. Okay. So for X val in XX and for Y val in YY. And then what I'll do is I'll choose the number C, which is equals to XX plus 1J times, X val times 1J times Y val. So now this creates my matrix, which is like the complex number, which is x plus 1y. Like the real part is x and the imaginary part is y. And once I have this, I will call is Mandelbrot and will pass c to it, which is this complex number. And now I will turn this to an integer because this returns true or false. So if I turn this to an integer, then I know what it is. And then now I can show you what happens is this. So for example, if I convert an true to an integer, I get 1. And if I convert false to an integer, sorry, if I convert false to an integer, I get 0. So that's what will happen in here if I convert 0 and 1. And then let's find out what we want to do. So now we also want I value and j value in here. And for this, we are going to use enumerate. So I'm going to also explain what this enumerate means. Okay. So before again I explain this code, let me give you a simple example of what enumerate means. Then you will understand what I'm doing in here. So I can use a for loop for x val. So I can do, for example, I comma x val in, say, and I pass this enumerate. This is an inbuilt Python function, and I call something like a 5, 6, 7, 8. So what enumerate will give me is for I get the index number, and for x val I get every element. So for example, now if I give something like print I comma x val and hit enter, so you see what I get is 0, 5, 1, 6, 2, 7, 3, 8. So then what happens in here is that I get all the values of like yeah, here what happens is I get all the values of x in here. So for the 0th element, the element value is 5. So for x val, I get the element value, and for I get the index. So upon looking at this, I see that here, for example, I don't need it because I am going through every values, and for y, I'm going to every values as well. And now what I want in here is that my y should be along the rows and j should be y should be along the rows and the other should be along the columns, right? So I do something like a Mandelbrot I comma j is this. Uh, I missed the n. Okay. So now once this is done, I do something like a plt.p color mesh. I pass Mandelbrot, get rid of everything else. And let's also choose a color map which is better for this. So since we have just two values, we'll choose a color map which is this binary, say. So let's choose a okay. And then we'll just do something like a plt dot show just to show the plot in here. And sorry, this is Z prime. So at the end, we are iterating, and at the end, we are checking if Z prime is rather, we can actually get rid of this as well. This is not needed. And we do something like a Z is equals to Z square plus C. And we always check after the end. I think this is much simpler. Okay. So let's try this. So what this says is, okay, got it. So this is what I was thinking. It should be other way around. And then let's have this, and there it is. We have the Mandelbrot set created, just like this. So if you, for example, Google the Mandelbrot set, you'll see quite a lot of examples of how Mandelbrot set looks like, which is a clear example is here, for example, of how a Mandelbrot set would look like, and we have been able to generate something similar. So, for example, if you use something like a Viridis, you will perhaps see a better color thing to it. So yeah, and then if you increase your resolution, so this is like 100, 101, and if you like say use something like a 500, 501, perhaps you'll have something which is better. Let's see. Takes a bit of time, but as you can see, from the here to here, the things have improved much, and then you can have a better resolution in this case. Okay, so now I will not cover the next part of it, which is if you're feeling enthusiastic, you can do this and color the points according to the argument of the function, which I'll keep up to you to explore, but it is, I think, will be fairly straightforward to do. So is this part clear? Like what
Yes,
I
so I could not understand this XX here, and especially this is the outcome of the mesh split XX and YY.
Okay. So what XX is, okay, then let me give you a simple example and just to show you what has happened. So let's have say you have something like np dot array, something like 1, 2, 3, right? And similarly, we have something like a y, say something like a say 5, 6, right? So as you can see, we have created here two 1D arrays, which is 1, 2, 3, and 5, 6. So for what mesh grid will do is that for every value of x, it will create a value of take all the values of y and vice versa. So for example, let's try look at what mesh grid is doing by calling mesh grid on this too, and we pass x comma y. So it's kind of creates a mesh in that sense. And now you see that what you get are two arrays. The first array is this 1, 2, 3 repeated 2 times. And then the second array, you see, you have this 5 like repeated 3 times and 6 repeated 3 times. So then if you look at every point in here, you have 1, 5, 2, 5, and 3, 5. So what this would mean is that 1, 5, 2, 5, 3, 5. So for every value of x, you have like for every value of y, you have associated x with it. Similarly, if you look at the second one, you will have 1, 6, 2, 6, 3, 6. So you have 1, 6, 2, 6, 3, 6. So now is this clear, like what mesh grid is doing? It's like creating the mesh, having all the combinations.
Yes, so intuitively I could understand, but then, so what is XX here and what is YY here? Like,
So since there are there are these two arrays, right? So
hmm,
I am saying that the first array is XX and the second array is YY. These are 2D arrays.
yes, but then
Since mesh grid returns two arrays, I am assigning the first array of mesh grid as XX and the second array of mesh grid as YY.
yes, but then what is the meaning of XX here? It is just the, I mean, the
It's
two
a
D.
mesh of like 2D. It's a 2D thing. So for example, if you do something in here, say if you write XX comma YY equals to this, and then if you do XX, you will get the first one. You see 1, 2, 3, 1, 2, 3, which is this first one.
Yes, it's true, but then what is the meaning of this thing? That the
The meaning
first,
of this will be like say you have to match the things. For example, XX 0, 0 has to be matched with YY 0, sorry, 0, 0. So this is like a 2D mesh, right? So this is one set of points, 1, 5. So you can think of this like I have created a 2D mesh, and similarly, XX, say 0, 1 has the same, has to be a coordinate with 2, 5. So you see, you create kind of like a 2D mesh.
Okay.
So this is exactly what it is doing. So you can think of this as two array, like each of the element of this XX array and the YY array with the same, if you consider the same position in this XX array and YY array, it gives you in a mesh what is the coordinate of that particular mesh point.
Yes. Yes.
Like,
And why are we keeping the value of the y one more than the value of the x? I just
oh,
find.
okay. Yeah, so that this is just for me to check that the X goes along the rows and Y goes along the columns. That's all.
Okay.
Sometimes, like if I do not keep this equal, then it becomes difficult for me to check which is along the rows and which is along the columns. And if you keep this unequal, then it is easy for you to debug the code to see, okay, is the X that you want is really along the X axis, and Y which you want is really along the Y axis or not. So for example, if you remember, I was initially having error writing I comma J instead of J comma I.
Yes.
And you will not get that error, and you will run with I comma j fine, perfectly fine. Yet although the code will be erroneous because x and y will be then flipped, and which you can avoid just by doing 500 and 501. Then you will get an error because the two are unequal. And so if you want to assign x values to y values, then it will not happen. So at some point it will complain that you do not have enough number of points in y. So that's why I kept it like this way. So this helps me to debug the code if I have a problem. Otherwise, the problem will be overlooked. And then if you plot, and in your plot, if you really know, like in a real world problem, you really know that how the plot should come, then you will see that the x and y axis have flipped. Then you kind of do something like a transpose or something to fix that. But this is a good way to just from the beginning to ensure that the rows and the columns are exactly how you want it to be.
Yes.
This is just a trick for me to uh, just debug the code and do not have error just from experience. Okay, so let's think this is the last question that we have in here, question number 18, which is about least squares. So we can talk about this. And probably, I think we can then finish early today, since this kind of the end of a very long set of questions, and then we can start afresh from next week after doing this question. Okay. So let's start with this least square thing, which is like if you are collecting and doing kind of data analysis and doing a real experiment, then you also have experimental noise. And you have a theory which says how two variables like y and x are related. Then you want to test and fit your theory to the observed data and find out that how well is your theory explaining the data, and also kind of try to estimate some of the free parameters in your model or from in your theory with the real data. So this is exactly what this does. So for this, it is using something called Millikan's oil drop experiment, which perhaps you have come across in your +2. So this was like a Nobel Prize winning experiment done by Robert Millikan at some point, which is been used to find out the charge of an electron back in early 1900s. So let's take the data for this, uh, which will be, I guess, 18, the last one. Yeah, really small data. So let's copy this and create a new file. Let's call this txt, and files millican.txt. Okay, got created. Let's get rid of these variables. So let's load the data as always. np.load txt. This will be millican.txt. This is the data that we are loading. And now this says is that we need to find out the charge of the electron by using this data. So let's try to plot this and see what's happening in here. So for this, we will going to this plt.plot data. So the first row goes to the x-axis. Sorry, the first column, and the second column goes to y-axis. And then let's make a grid and show. So let's select plots and go in here. So yeah. So since these are data points, I'll do something like a KO just to not have the lines, but just have the points. So here it is. So I have the data points in here. Got it. So now let's see what this question says. In the online resources, you will find a file called millican.txt. The file contains 2 columns of numbers giving x and y. Read the program of the data points and make a graph of 1 dot for each circle of the point. So that we have already done in here. Add code to your program before the part that makes the graph to calculate the quantities ex, ey, exx, and exy as described above. And then, where was I? Yeah, as defined above, and from them calculate and print out the slope m and intercept c of the best fit line. Okay, so let's then try to code this up. So ex is nothing but the average value of all the x points. So let's do that. Ex is mp dot mean. So to find out the average, we just do this, and this is all the value of x points. So colon, comma, 0. These are all the values of x points. Similarly, ey is then the mean of all the values of y points. So let's copy this, paste this. So the y values are this, and we will call this, sorry, ey. So once we have found ex and ey, we will do xx, x square. So exx is then the average of colon, comma, 0, just a 2 whole square. And similarly, the other one, exy, is just the average of x and y's. So it's colon, comma, 1. Right. So this is the average of xi, yi. Right. So once we have done this, it says that we have to find out the values of the slope and the intercept, right? Which is also given here, which is just minimizing what is known as the least square using or chi-square using this. So minimization of chi-square gives you this value of m, which is e x y minus ex times ey divided by, this is something, divided by exx exx minus EX whole square. This is M, and similarly we want C, which is the intercept, and this will be EXX times EY, EXX times EY minus EX times EXY minus EX times EXY divided by EXX minus EX square. Okay, so we have got the slope and the intercept of the best fit. Now I'll write the code that goes through each of the data points in turn and evaluate mxi plus c using the values of m and c that you have calculated and draw the solid line on the original data. You should end up with the data point that a straight line that runs through them. Okay, so let's now do that. So we know the slope. So then we do a plt dot plot for x. Let's get rid of these. We'll do something like a data colon comma 0. So these are the values of x. But for the value of y, we know m times, instead of the data, our model is what we are going to use. So we choose m times x plus c is my y values, right? And you can choose a color. So let's say color equals to tab blue. This just gives me a blue color line through this data. And I do a plt.show. So let's see how this works out. So as you can see, we have found out the best fit line, which passes through all these data points. Okay. So once we have done this, the idea here is that your slope m is going to have the value of h over e, and phi has the value of your work function. And from this, you can really get to find out the charge of an electron by trying to find out the MNC. So the MNC has the charge of the electron buried in it. So I'll not go into discussing the physics of how this is happening, but this is just to demonstrate the process of doing least square fitting. So is this point clear in here? Is this clear?
Yes, yes. It's like
Okay.
regression.
Exactly. Yeah, least square fitting is just one kind of regression, which people do generally. Yeah. Okay. So I think we are done for today because the really large exercise is over. And then from, I think, next week, we are going to start with the next set of exercises and go slowly move on to different aspects of computational physics and also using Python. So if you have any questions, and meanwhile, and if you are stuck with something, want to clarify, you can always feel free to post on Teams, where I actively check what's going on. So yeah, so I think that is all I had to say for today. And goodbye, and have a nice
But
weekend.
thank you
Yeah,
so much.
yeah.